Chapter 26, Capacitance. We've moved through the 3 chapters that have basically laid the foundations for electrostatics. Now we're starting to get into some applications. And when we get into applications, that means we're going to get back to doing some labs. So we will have a lab later on this week. So, capacitance, or the device, a capacitor. This is a circuit device, and kind of developing the logic of what it does. Imagine I have a conductor. So here is my, let's say, just conductive plate. Now, if I want to charge this up, I can take it. I'm going to assume, let's say, we're going to charge it positively. You can charge it positively by removing electrons. Now, you build up charge. That charge is going to be evenly distributed because the remaining electrons will kind of shift around. So, on that conductor, it'll be reasonably evenly distributed. In actuality, a little more charge will gather towards the edges than towards the center, and we'll talk about that. However, when you build up enough charge, it will start to affect the air around it. When it affects the air around it, it'll start to ionize the air when you have enough charge, and you get little static discharges. Well, we can bring a second conductive plate in here. And with this second conductive plate, I'm not going to put any charge on it. However, I am going to ground this plate. Okay? And by grounding it, it's connected to a place that can supply electrons or can accept electrons. There are enough charges in what it's connected to that it can either receive, okay, or send electrons out. Well, if I bring that second conductive plate near the charged plate, then it'll be in the electric field. And being in the electric field of the charged plate has a charge of that is positive. Well, that's going to attract electrons. So we're going to get some electrons that flow up into here. Okay, and it's going to charge up. In fact, if I increase the charge on my first plate, I will also get an increase in the charge on my second plate. And what turns out is when you place 2 conductors near each other, but very key, you have to, in here, have something that stops the charges from just transferring. So you place 2 conductors near each other that are separated by an insulator. This actually enables you to build up more charge than if you had just had the single conductor. So this device of 2 conductors near each other separated by an insulator, this device is called a capacitor. So we will get into applications and uses of capacitors. For right now, what we want to understand is basically the idea of a capacitor, what different capacitors look like in circuits or devices like these. And we'll take a look at some circuit boards so you can identify different capacitors. Now, notice on here, if I can highlight a little bit, right in this neighborhood on that one, you have 10, the micro symbol, and an F over probably the one all the way on the left. If I highlight right there, you have 1,000, the micro symbol, and an F. Your unit of capacitance is a farad. A farad is very, very large. And so oftentimes we deal in smaller amounts. We deal in microfarads. Remember, that's 10 to the negative 6. And sometimes even picofarads, which would be, nanofarads, small n, 10 to the negative 9th, and picofarads, 10 to the negative 12th. So get used to perhaps seeing a couple different metric prefixes than what you were used to dealing with. Now, let's get a little bit more into the idea of a capacitor. It is a circuit device on the most elementary level. It's a circuit device that is there to store charge, but that's a very elementary way of thinking of it. We're going to get deeper than that. It consists of your two parallel conductors separated by an insulator. Capacitance is a number that's used to describe a capacitor. And again, on the simple level, that's the ability of a capacitor to store charge. So if you have a higher capacitance, you have more of an ability to store charge. Okay, so if we consider a simple capacitor configuration, I have a conductor and another conductor, and in between them I have some type of an insulator, which I'm just going to highlight so I can draw in there. So that is an insulator that is in the middle there. More proper term is dielectric, and we'll get more into specifics on that. If I place a charge of positive Q on one conductor, then I'm going to get the same amount of charge balanced on the other side. In other words, I'll have a negative Q on that side. Okay, now, if I have that difference in charges, well, that sets up an electric field. If I picture a little positive test charge between the two plates, it would move from the left side to the right side. So within here, there is an electric field that is established. Now, the purpose of that insulator in there is to prevent the charges from flowing, so nothing actually ever flows across or between the plates of the capacitor. If it does, then you take the capacitor out and you throw it away because you've just fried the capacitor. Now, if we have a field across there and there is some distance across between the plates, then by our add equation, V equals negative ED, we have some potential difference between those plates. If we increase the charge on the plates, so if I add some more positive charge here, well, that means I'm going to get more negative charge balanced over there. If I increase the charge, I'm going to make the field stronger. And if I make the field stronger, V equals ED, I'm going to make the potential difference greater. Okay, what we're most interested in here is the charge and the potential. They change together, okay, or they are directly proportional to each other. Well, if they're directly proportional to each other, then all you need is a proportionality constant between them. That proportionality constant to set up an equation is capacitance. So capacitance, as we said, it's the ability to store charge, but more specifically, it is a proportionality constant. It is the ratio of the charge on one plate of a capacitor to the potential difference between the plates. So then C is your symbol for capacitance, Q is your symbol for charge. Typically with a capacitor, a capital Q is used, and V is your symbol for the potential difference. So then C is the constant. Once you set the given configuration, this is a constant for a certain geometry, for a certain configuration of conductors and insulators. So then if we go back to our diagram on the capacitors, the one on the right side, 10 microfarads, that's why it's printed on there. It doesn't change. You can put a little charge on it, you get a little voltage. You can put a big charge on it, you get a big voltage. Okay, but that's the constant. Now, you may also notice below that 35 microfarads, it says 35 volts. Well, that's the maximum voltage that capacitor can have before the electric field that you set up actually starts to break down the insulating barrier inside of that. Okay, so then our base equation right now for capacitors is C is equal to Q over V. Capacitance is equal to charge over voltage. Ponder physics.